Good morning, everybody. Welcome back to lecture number 27. Next week is the last week. We have 3 full lectures, right? So quiz 5 will be on Tuesday. It will cover chapter 13. After the major exam, before the major exam, the Thursday before the major exam, we will have quiz 6, and it will cover everything. Most likely the power part. We'll have questions from the power part. Then the lecture on Sunday after the major exam, there will be no lecture. Okay? Get it? You get the plan? Okay.
Major about what?
Yes. Major on Saturday, April 12, 6:30 p.m. Okay? Any question? You don't want to have quiz before the major? Who doesn't want a quiz?
After the major.
Who has quizzes after the major? Do you want to come 1 hour before and do a quiz 1 hour before the major? Okay, خلاص. No, let's keep it the plan as it is. Maybe I'll change it, but for now, for next week, we know the plan, okay? So before we start, let me revise this slide because somehow it's relevant today. When we have ideal voltage source, we have a battery and a source, or a function generator and a source. All of you now know what's a function generator. In practical situations, the voltage source has impedance at the beginning. Okay? Now, if the internal resistance or impedance is somehow relatively large compared to the resistive load, for example, if this is 5 and this is 5, half of the voltage will be consumed inside the voltage source. Get it? VDR. Get it? Hatim Asiri, did you get it? Okay, that's why. Voltage source has an internal resistance of 5 ohms, and the load is 5 ohms. Using VDR, 5 volts will appear here, 5 volts will appear here, 50% here, 50% here. So we're wasting 50% of the load of what could have been delivered to the load due to the high internal resistance. This is a very important concept, is always we want to have very small internal resistors for the voltage source. Get it? Now, so the ideal voltage source has an internal output resistance equal to 0 to drive as much as load as possible, but in a practical situation, this is not always the case. For a current source, ideally we have a current source. This is a current source, but this is another symbol. They put voltage source with an arrow. What did we use? Is just an arrow. An arrow and a load, okay? Practically, there is a shunt resistance called RS that we can connect it to the load. Okay?
What's the point of having small resistance inside the voltage source?
What do you mean?
Double case. And what's the point of having small resistance?
No, هذا داخل في البطارية. Feature inside the source. For non-ideal situations, يعني في cables connected.
Oh, okay.
If you have a function generator, it has internal resistance cables. If you have a battery, it is too old that it looks like there's an internal resistance. يعني مش 10 volt will apply to the load. Some of it will be consumed internally. Same for the current source, but this is not relevant for today's lecture. What's relevant for today's lecture is this case. Okay? Now, last time we talked about the design of simple amplifier. And what did we say the range? From 1 kilo to 1 mega. It's 1 kilo? Yeah, from 100 ohm to 1 mega. What did I tell you? If you get stuck, use kilo ohms, okay? If you use kilo ohms, you will get currents in milliamps. If you use 1 or 10 or 15 ohm, you will get currents in 1 or 2 amps, which is too large for the op amp. Get it? Get it? Now, we usually find the combination for a summing amplifier design. The issue we had is that getting number 5, positive 5, is not going to happen unless VA is already negative, because the ratio of two resistors is positive. So the solution is to use non-inverting amplifier to invert the input, and then use a summing amplifier as stage 2. Okay? And you come up with a design. There is no definite answer to that. For nonlinear limitations, everything is not included except the clipping, which we can summarize it in this slide and this slide. So in the exam, anything after that, anything after that is not required. Okay? So what is clipping? The output voltage range is limited. If input signal is sufficiently large, then the output. What drives the limitations? 15 and minus 15. Get it? So if you have an input of 5 and a gain of 20, your output should be 20 and minus 20. Because the supply is 15 and minus 15, it will clip just before 15. Not at 15, just before 15. Maybe 14.5, for example. Okay? Now let's say it will clip at 15. If we ask you a question in the test, 1 plus R2 over R1, supply is 15 plus some minus. Okay? Maximum input equals to, we don't know. Okay? And I tell you the gain, I tell you R2, R1, both are equal, let's say, to 1 kilo. Okay? Get it? So what's the gain? It's 2, right? 2 times 15 is what? 30. Okay? So if I put 15, I'll get 30, clipping immediately. The question is, what is the maximum input I can have in order to avoid clipping? And I give you answers. 9, 8, 7, 6.8. I don't know. E, I do not know. What do you see? What do you say?
7.
Not really. Be careful. If you put 7, oh, not 7. I got it. Perfect.
7.4.
Why?
Because 7.5 it's already clipped.
If you put 7.5, you will already be clipping. Get it? It has to be below. So a good number is 7.4. Why? 2 times 7.4 is how much?
14.8.
14.8. Now let's pretend that this is 14.8. Okay? Ideally, you should have it even lower, 7.3, 7.2. Get it? Who doesn't get this example? Raise your hand. Nassar, did you get it? Why we did not pick up 7.5? Because if you put 7.5, it will be at 15. At 15, you're above the clipping. Get it?
What if we have above the clip? What will happen?
It will be clipped. يعني, in very extreme situations, you will have an output that looks like that.
Isn't this exist in real life?
Yes, it exists. You can't get more than the supply. That's the rule. But in reality, due to non-ideal situations, it's actually, if the supply is 15, it will be even lower.
Like efficiencies of the pumps.
Similar to that concept, okay? So if we bring you a question in the test, what will be R2 over R1, and we fix the input the input voltage? Can you design R2 and R1? Basically, you have to change the gain, find the gain that doesn't give you clipping, and then -1. Remember, this is what? A non-inverting amplifier. You have to memorize now يا حاتم the non-inverting amplifier. هذا ايش non-inverting amplifier. خلاص حفظنا شكله. Get it? Okay. I'm going to walk over the next slides. This slide is similar. Yes.
ليش مو عن اللينير limitation؟
Non-linear limitations يعني it's not linear with the input. For example, you don't get the clipping linearly changing. You get it suddenly, non-linear. Get it? There are other factors in the, for example, the frequency rate of the change will show it, but it's not required. This slide is very similar, but this is another idea, is you have to get R1 and R2. You have to calculate the gain. 1 plus 3 over 1 is what? 4. So the gain is 4. Get it? So the output, if you have an input of 1, do you have clipping here? No, because the maximum is 1, so you get 1 and -1 times 4, you get 4 and -4, you're away from the clipping. Okay, that's a good example. When do you have clipping? Is, for example, this is another example where we have a clipping, that's the 14. If you have the gain of 4, 4 times 5 is 20, you get clipping. So just make it below. It's a design problem. Don't make it exactly at the 15, make it just below. Okay? This is not required, but let's try to learn it, okay? One of the limitations is I already told you 100 times, you have the car stereo system. You cannot connect very big speakers to your car. I'll give you an example. Okay? All of you know Yaris, small car, صح? All of you know, give me a name of a big car. Land Cruiser. So Land Cruiser, it can, op amps اللي في Land Cruiser, they can deliver high current. السماعات تكون محترمة، مو زي السماعات حقت يارس اللي هي يعني تمشي الحال. If you cannot drive the load, if you cannot drive the speakers, for example, if you cannot provide enough current, then we will have the problem is the maximum current the op amp can deliver. You cannot, no matter what you do, you cannot deliver. The op amp has to be more expensive one. Now, how do you know the maximum current? You have to go to the data sheet. For example, LM741 model, the limits are plus or minus 40 milliamp. It means if you try to get 60 milliamp, 7 milliamp, you will not get it. And what determines that is the RL. For example, here, suppose that we set the peak input voltage to be 1, adjust the load resistance to be 50 ohm. For ideal op amp, you will get 1, what was the gain? Okay, 1 times 5. So 5 over 50. Okay, the V output is 4. 4 divided by 50. Is it 80 milliamp? Oh, we have to calculate the gain, I guess. What's 4 over 50?
0.8.
Okay, so 80 milliamp. They are already telling you in the data sheet the maximum is 40. So you will not be able to drive the voltage. So you will get another form of clipping, okay? So what will happen? What's the solution? The only solution is to reduce your RL, okay? Is to increase your RL. I'm sorry, to increase your RL. If your RL now is 40 over 100, you will get 40. I don't know, I don't have calculator. Yeah, 0.04 times 1,000, which is 40 milliamps. So if you make your load larger, 100 ohms, then you will be able to drive it. Big stereotypes, they will have a smaller impedance or larger impedance. What do you think?
Smaller.
They have smaller. So small stereos, they have larger impedance. They draw less current. They draw less current. Okay? This is not required in the exam. فائدة. Another thing, so this is also non-linear, yeah, Adnan, because it depends on the load and there is no linear relationship that tells you when to stop. It becomes all of a sudden if it's above or minus 40 milliamp, the I load. That's why it's non-linear. The other thing which is also not required is if you provide a signal with high frequency, for example, there is certain spectrums in the music that cheap headphones you can hear it, you cannot hear it, but expensive headphones you can hear it. Get it? That sometimes if you play some music, cheap headphones would clip, would not give you enough quality of the signal. It will eliminate certain frequencies. This has to do of what we call the change of the voltage as a function of time. So if the input is sinusoidal, that changes very quickly. Sometimes the op-amp cannot catch up. The rate is smaller, so you will have triangular shapes rather than sinusoidal shapes. And if you have, for example, the input is very fast sinusoidal, okay? High frequency signal. The op-amp trying to amplify this, but all of a sudden it gets down, it gets down, it gets down. So it will be like a saw shape because there is always a delay in changing the output. Because the input signal is too fast, you only capture only this part of the sinusoidal to be amplified. Then we will have a distortion, a non-linear distortion. Get it, Turkey?
Yes.
If you have very high frequency signal with a cheap op-amps, you cannot hear that frequency at the output. Okay? Because it needs some time to catch up the signal. This is not required in this course. Okay? Just think about it, okay? Cheap headphones versus expensive headphones. Cheap car versus expensive car. The only thing that's required is up to slide 38. Now, I'm talking about this section, the nonlinear limitation. Any question about the nonlinear limitation? Okay, Michelle, what is the required part in this course for the nonlinear limitations? No, the concept. Summarize to me what's required. Just voltage clipping. Okay? Voltage clipping means you have to make sure that the gain times the input does not exceed the supply. Okay? And we can ask all sorts of questions similar to this question in the test. Anything else is not required, فقط للفائدة. Okay. Now our favorite subject, differential and instrumentation amplifier. Do you guys know the major, control, and instrumentation? There's a major at KFUPM.
Oh, yeah.
Do you know this major?
Yes.
What's your opinion about this major?
Easy. Very easy.
Very easy? Okay. Why you guys did not go there? You want to know a story?
Yes.
Or a lecture?
Story.
Story? Let's give you some story. Get me from a lecture. So when I was junior, okay, I got my first internship with Aramco, okay? I got the assignment page, and the title of the group was Process Automation, okay? I think it was called group. So whenever we hear the term automation and the process together, it's another fancy word of saying control and instrumentation. Okay? What is here in Saudi Arabia? What do we mean by control and instrumentation in terms of industry?
Oil and gas.
Oil and gas, mainly. So you usually have a process. There is input, there is output, then you have sensors here, okay? You have sensors here, sensors there, I don't know, flow sensor here, stuff like that. So the story I had is, I told them I'm not a chemical engineering student, I'm electrical. Why did you put me in this group? But it turned out this field, we had 3 engineers from 3 areas. My supervisor was what? Mechanical engineer. And I was electrical engineer. And the guy next to me was a chemical engineer. So if you plan to work in the field of process automation, أتمتة العمليات, which is a more fancy word of saying control and instrumentation, you have to work with electrical, chemical, and mechanical. And to prove that point, they changed me later at a different assignment in gig plants. Do you know gig? Who doesn't know gig? ما تعرف gig؟ من أهل الشرقية ما تعرف gig؟ Who does not know gig? Gig. Okay, who doesn't know gig? Okay, gig has the largest oil processing facility in the world. When I joined them, I joined a group called System Support Unit. And again, this is another fancy word of control and instrumentation. And in this group, we had mechanical, chemical, electrical, and software working together in one group. Bottom line, what I want to say is probably in the field of control and instrumentation, the easy major, they try to get every small aspect from every major. One aspect they take from us, the concept of instrumentation. What do you need to measure, for example, the pressure? You need sensors, right? So you have what? I don't know how to draw a pipeline. Let's say this is a pipeline, okay? You have to put sensors here. So here we have sensor 1, here we have sensor 2, صح? صح? You measure the pressure here, you measure the pressure here. But the question is, when the fluid pushes into the sensor, we call it the transducer, and when it touches it, the fluid touches it, how would they translate the actual mechanical vibrations, the mechanical pressure, into the electrical component, the circuit? How would they translate it as a form of measurement? They convert it into a signal, right? A signal, sinusoidal signal, whatever. Higher signal means higher pressure, smaller signal means lower pressure. But again, to know the pressure, you need to measure the difference between 2 points, right? For example, here if we have very high pressure, and here we have very high pressure, we subtract them, we get what we call the pressure difference, right? Which could be more, is less variations, it will be mainly around the norm, okay? If you have a certain pressure increase, the difference is higher, you will have higher pressure. Something like that, okay? The key point here is you need to subtract two values of measurements. Let me repeat. To measure the pressure, you need how many sensors? How do you convert the actual pressure into signal? Using circuits, right? What component of circuit that does this conversion? The op-amp. So here, for example, the actual voltage that appears from the pressure of signal 1 and signal 2, you subtract them, then you can get some sort of an indication of your measurement. So it converts the difference between input 1 and input 2, eliminates whatever noise, eliminates the unnecessary information, and you subtract the difference. Another example is مثبت السرعة في السيارة. مثبت السرعة you have a speed 145 and you're setting it up at your speed is 144, مثبت السرعة 145. Do you want to amplify 145 and subtract it from the amplified signal of 145, or you want to subtract the two signals and amplify it? Subtract the two signals and amplify it. So sometimes it's better for us to subtract the two information and amplify it to remove the noise.
نفس غدارة الاتصال. نفس غدارة الاتصال.
I don't know how they work, but I think it has to do with the concept of differential. They measure the difference between the reference speed and the speed, and then they amplify the signal. Okay? So we have two amplifiers in section 13.8. The first one is what we call differential, and the second one we call instrumentation. So the output is the amplification of a small reference between two input signals. You have two input signals. The output voltage for the below circuit is R2 over R1 times V1 minus V2. We will show you the derivation later. Why the differential amplifier is important? Because we need to find the difference between two small signals in a noisy environment. Sensor 1, sensor 2. You combine the two signals in a very noisy environment, and then you amplify that difference. That's how control instrumentation works. If we have two small signals applied to the amplifier, approximately V1 and minus V2 are equal, there are some noise will be added due to the non-ideal environment. For example, in the pressure you might have noise from the machines, you might have vibration of the actual pipeline, you might have air, wind blowing outside the pipeline, etc. These are noises. And if they are common in sensor 1 and sensor 2, you will subtract them, but you only keep, the only needed information is to keep the difference between the pressure. And that's how you get the pressure in the pipeline. Get it? Get it? So why do you subtract? To eliminate the noise in an unideal environment. Okay? Why? Because the noise is added to V1 and V2 together, sensor 1 and sensor 2. They usually have the same noise. Same pipeline, same vibration, same wind, same temperature. The only thing that's different is the true information of pressure difference. Okay? The difference between V1 and V2 will be amplified, which the noise will be cancelled. We call it common mode rejection ratio. common mode. ايش معنى common mode؟ common exam. ايش معنى common exam؟ جريدات نفس الشيء مشترك. So common mode, they have the same mode of environment. Think of it that way. Sensor 1 and sensor 2 in the same pipeline, in the same process. Rejection. What does rejection mean? Rough. If you subtract the common noise, you're rejecting it. And ratio is how much you're rejecting that noise. There are highly sensitive sensors, there are low sensitive sensors. There is, if the amplification ratio is high, you can reject more signal and vice versa. Okay? Let's look at the circuit, okay? The Now we will do another exercise. I'm gonna draw it. So we have here, in the positive input we have, now he's telling you R4 equal to R2, R1 equal to R3. Get it? So I'm gonna call this R2, I'm gonna call this R1, and here we have plus and minus V1. Okay? On the other hand, in the negative input, we have just R1, and here we have V2. Then we have a feedback, negative feedback to R2, and we're connecting it to an open circuit V output. There is no R load. So we are professionals. Let's put the signal. So here we have I1, right? Plus some minus. Do we have a, okay, here we have I2 plus some minus, plus minus, plus minus, here we have I3. Do we have a negative feedback?
Yes.
So we have SPC, summing point constraints. So the voltage here is similar as the voltage here. Let's call this Vx, okay? So what's the voltage here? Also Vx. So the voltage here is same as here. Also we have no current, I is 0 here. I is 0 here. Is it complete?
ليش مو ground؟
Because there is a resistor here. And I will explain it now. You will not see ground every time. If you don't see a ground, don't put a virtual ground. Get it? Okay. How do we start? We need to think. How many inputs do we have? We have V1 applied to R1 and R2. I here is 0. So R2 over R1 plus R2 will appear here. Voltage divider rule. Get it? So R2 over R1, R2 over R1 plus R2 times V1 will also appear here. In addition, we have a current I2 here moving, which is equal to I3. So let's analyze this circuit. So I will start with V1. So what is Vx? Vx equal to R2 over R1 plus R2 times V1. Do you all agree with me with that? Okay. Then we have I1. What is I1? I1 is V1 over R1 plus R2. Get it? V1 over R1 plus R2. Why? It's Ohm's law. Because all of I1 will go here. There is no I1 going there. Get it? Then what do we have? I2. What is I2? I2 is V2 minus Vx over R1. V2 minus Vx over R1. Oh, but it equals to I3, right? I2 equals to I3. So I3 equals to what? Vx minus V output over R2. Vx minus V output over R2. And I know that they are equal, so I should make it like that. V2 minus Vx over R1. What's my goal? My goal is to write V output as a function of V1 and V2. So I have to separate V output here, and I have to separate V1 and V2 here. It means I need to remove Vx. But we already know the formula of Vx. Get it? Mashal, get it? Remind me your name?
محمد
Hamad ايش؟
إبراهيم
Ibrahim. I need your help. Algebra. How do we do this? I want to write V output on the left, V1 and V2 on the right, and I know Vx is a function of V1. So let's separate them. So we have here what? Can I do V output here? So minus 1, let's do it this way, times V output, and I remove Vx here, equal to V2 over R1 minus 1 over R2 Vx minus 1 over R1 Vx. Can I do that?
Yes.
Burassar, can I do that? Okay. Can I do,
Multiply by minus R2.
yeah, can I do multiply by minus R2, so this will be minus R2 over R1 V1 plus R2 over R2 Vx plus R2 over R1 Vx. Can I do that? Okay. Can I also do minus R2 over R1 V1 plus, I take Vx as a common factor, and this will be 1 plus R2 over R1. Can I do that? Okay. Can I erase this circuit now? Now I know that Vx equal to R2 over R1 plus R2 times V1, right? And what was the signal here, V output? Minus R2 over R1 V1 plus Vx, what is Vx? R2 over R1 plus R2 times V1. Wait a second. I think we have an issue. We made a mistake here, Shabab. This is V2. This is V2. Okay, we made a mistake. So this one is what? V2, right? Times 1 plus R2 over R1. توحيد المقامات حقت هذا. Minus R2 over R1 V2 plus R2 over R1 plus R2 times V1 R1 plus R2 over R1. Can I cancel this and that? So what would be the output? R2 over R1 times V1 minus V2. Get it? I'm gonna resolve this example عشان يعلق في المخ. Do we have a ground here at the positive input? No, we don't have. What do we have here? We have R2, so R4 is R2, R3 is R1, so we have R2 over R1 plus R2 times V1 appearing here. We also said I2 is V2 minus Vx over R1 equals to Vx minus Vo over R2. Then we substituted what is Vx here, and we separated R2 and R1 between left and right. We had to make sure that there is a negative feedback here. We have inverting input at V2, non-inverting input at V1. So if you look at the output, V1 is always positive, V2 is always negative. But there is a problem with this circuit. The problem, if we have voltage source that has a resistive load, if you have R1 and R2 small enough, you will lose some voltage. So the problem of the previous circuit, if the voltage sources have internal resistances, which we explained at the beginning of this lecture, the output for the common mode signal does not equal to 0. If you do the math, the output will always be a non-zero output. What does it mean? It means if you have, because of this voltage divider rule at the beginning, because of this VDR, RS will be added to R3, RS will be added to R1, and you will always have a VDR, then your output will always be non-zero. You don't want to have a non-zero output all the time. Why? Because it's confusing, and you're wasting energy all the time for the sensors. Then the sensors, if they have that battery, they will drain. So you want your sensors to have 0. If there is a change in your signal, you want to have some sort of output. So the problem comes from what? The internal resistance of the sources. What could be the internal resistance of the source? It could be the internal resistance of the transducer that touches the fluid in the pipeline. This is for example. An improved differential amplifier circuit for which the common mode rejection ratio is not dependent on the internal resistance of the source is using 2 stages. Again, our problems in op amps are better solved with 2 stages. The currents drawn from the signal sources are 0, hence the output voltage from the source is unaffected by the internal impedance. Okay? Notice that the second stage of the instrumentation amplifier is a unity gain. So do you recognize this circuit?
Some,
Do you recognize this circuit?
yes, some.
No, it's similar to this circuit. Except we have R1 equal to R2 equal to R3 equal to R4. Right? R. So what's the output here? The output here will be 1R over R times V1 minus V2. Yeah, Shabab, this output here, V1 and V2, is at stage 1 and stage 2. I'm talking about only this stage. What's the output of this stage, stage 2? Equal to 1 V1 minus V2. This is only stage 2. So you recognize this amplifier? It's the previous slide. Now, we have here inverting or non-inverting amplifier. It's a tricky case, right? So we all recognize the second stage, but we do not know the first stage. Let me erase the board. So an instrumentation amplifier is the one that is implemented in the field. And it is standardized with these 2 stages. So for the first stage, we have both non-inverting inputs. You have a feedback here, so you have I1. What is I1? I1 equals VO2 minus V2 over R2. We have a negative feedback, so V2 will appear here, V1 will appear here, because of the summing point constraint. I1 equals to I2. What is I2? V2 minus, they call it here VA over R1. Similarly, with I3 equal to V output 1 minus V1 over R2 equals to V1 minus VA over R1. This is I3 equals to R4. And I'm telling you, the output here is VO1, the output here is VO2. What's the output of the second stage? Second stage, V output equals to 1 times VO1 minus VO2. VO1 minus VO2, because all the R's are equal, are identical. This is what we call unity gain, and gain is 1, differential amplifier. If your goal is to write V output as a function of V1 and V2. Okay? Your goal is to find VO. What time is it? We don't have time. So to do algebra here, you know that this is VO over R1, this is VA over R1, which implies that you can rewrite this. Let's start by rewriting the first equation, V output 2 minus V2 over R1 equals to 2 over R1 minus VA over R1. So V output 2 over R1 equals 2V2 over R1 minus VA over R1. R1 here we will multiply it, so V output 2 equals to 2V2 minus VA. Similarly, we have V output 1 minus V1 over R. What's this? Is this R2? Oh, this is R2. My God. It's not that easy. We don't have time. We'll finish it next lecture if the time is over. This is V2 over R2 plus V2 over R1 minus VA over R1. The other circuit will be VO1 over R2 equals V1 over R2 plus V1 over R1 minus VA over R1. Okay? When you plug VO1 here minus VO2 here, what do we have? Again, it's V1 over R1 plus V2 over V1 over R2 minus VA over R1 minus VO2, which is minus V2 over R2 minus V2 over R1 minus is VA over R1. The VAs will cancel, and then you will have 1 over R1 plus 1 over R2 V1 minus V2. We'll continue with next lecture. Okay, we don't have time. I don't want to interrupt you. It's 10:50. Any question?